Video we have some more terminology that we're going to need when talking about graphs. The first is adjacent here, and that is when you have points on the graph that are connected. So we'll look back at the bridges of Konigsberg here. Look at that graph. Since A and B have at least one connection between them, A and B are considered adjacent. Similarly, B and D are adjacent, and so on, whereas A and C are not adjacent here. So for our definition, that is, two vertices are adjacent if there is an edge. If there is an edge connecting them. The neighborhood, this is the set of all vertices adjacent to a given vertex. So the idea is that each vertex on your graph has a neighborhood. For this graph up here, the neighborhood of vertex A would be B and D, because that is all of the things that are connected to A. On the other hand, the neighborhood of B would be A, C, and D, because that's all the things that are connected to B. So you see, the neighborhood is going to depend on which vertex you're talking about, and it's going to change based on that. Finally, the degree of a vertex is the number of edges connecting to it. So up here in the same graph, the degree of A would be 3. And the idea is, you can imagine trying to draw a circle around the vertex and ask yourself, how many edges does it cross? It crosses 3 of them. And on the other hand, the degree of B would be 5, because it crosses 5 edges here. I do want to point out that if you have a graph that has a loop in it, let's say a simple graph like this where you have a loop at 1 and then a single edge connecting 1 to 2, in this case, the degree of node 1 would be 3, because that loop there gives us a total of 2 degree counting on that point. So just keep that in mind. And then we give this the Handshaking Theorem, which I think is one of the coolest little theorems we have in math. It says that if you have any sort of undirected graph, and that there are m edges in the graph total, then you are always going to get 2m equals the degree, sum of the degrees of the individual individual vertices. So up here, we did degree of A and B already. Let's do degree of C is 3, and degree of D is 3. And if you add them up, the total, right, this is what this symbol means in math, the total, if you add them up, you're going to get 14 here, which is the same as 2 times 7. And we said before, there are 7 edges in the bridges of Konigsberg graph. And the reason why this theorem is true, it's one of the most straightforward theorems in math, is that every single edge in your graph, if you look at it, it's going to connect to 2 vertices. Now, those 2 could be the same vertex using a loop here, but they're going to connect between 2 vertices, which means every single edge is going to give you a +1 degree on one side and a +1 degree on the other side. So every single edge is going to add 2 to the total degree. So that tells you that the total degree of everything is going to be just equal to 2 times the number of edges. Okay, last couple of things on this slide. Talk about subgraph. So a subgraph is when you take a graph and remove any number of edges or vertices. So we had a graph up here that was the bridges of Konigsberg. And if I wanted to remove one of the edges, let's say I remove that edge, the result is a subgraph. Let's say I want to remove more of that. I want to remove this vertex over here too. Now, if you remove a vertex, you have to remove whatever edges that are connected to it. Otherwise, you have lines going nowhere. And so this would also be a subgraph. And furthermore, even if you have the entire graph where you didn't remove anything, that is trivially a subgraph of the original graph. It's kind of like subsets. The whole set is a subset of itself. It's the same concept here. And then the last one here is called bipartite. And this one's a little tricky. So a bipartite graph is when you can separate the vertices in two groups and there are no connections inside either group. Now I need to give you an example of this here. So I'll clear a little bit of space on the side. So the idea is if you have a graph where you can draw it in such a way that all of your edges are between them and there are no individual edges on either side. So you notice how the left side here, there's no edges going between A and B, and the right side, there's no edges going between C and D. And so this is what's called a bipartite graph, is that you can split up your graph into two parts and you have connections between the two parts, but you will not have any connections completely within one part. And there's a really cool way of telling whether the graph is bipartite or not, and that's called coloring. So the idea is you pick yourself a color. So let's say I pick this here, and you color some of your edges that one, and then you pick a different color, and you color the other edges that one. And as long as you can do it in such a way that you never have an edge between two vertices of the same color, then it is bipartite. So notice how there's no connections between two yellow vertices, there's no connections between two orange vertices. However, if you look at this graph up here with the bridge of Konigsberg, if I color this, let's say A here, if I color it yellow, now it doesn't really matter what color I use, but I color that yellow. Well, anything that is connected to it has to have a different color. So since B is connected to it, I would need to use orange here and orange here, because they're both connected to A. And then at that point in time, I see there's a problem. Right here, let me use a different color. Right here, I have a connection between two orange things. So what that means is I could not have both of those being orange, but they also can't be yellow because they're connected to the top, which means two colors is insufficient for this graph, and so this graph is not bipartite. So if you can do it only using two colors, then you are guaranteed to be bipartite, and if you cannot do it with only two colors, it is not bipartite. Now you might be curious, well, how many colors do you need? On this particular graph, you would need only 3 colors. And you might be able to find a more complicated graph that you need 4 colors for. But it turns out there's a famous theorem that we aren't really covering in this class, but I'll mention it. It's called the 4-color mapping theorem. Is that if you ever have a certain type of graph, it's guaranteed that 4 colors is enough. You won't need more than that. So it's kind of a cool concept that this one we needed 3 colors, but it turns out 4 is the maximum you might ever need for this type of graph.